So hi everyone, we're the Self-Supervised Learning with topic models, and today we're presenting our final presentation. So as a project overview, we'll deal with two main concepts here. So the first is self-supervised learning. So it is a machine learning concept technique that does not require much manual labels, and it does so by implicitly generates some data and label pairs. So it actually saves lots of work. And the goal is to learn a representation useful for downstream text. And the other concept we're dealing with is the topic models. Specifically, we're dealing with three kind of topic models. The first is a pure topic model, which we only allow for one topic for any documents. And second, we're dealing with latent Dirichlet allocation model, in which we allows for multiple topics. And lastly, we have correlated topic model, in which we allows for correlations among topics. So the general goal of our project is to use neural network to learn a representation from which we can recover the posterior probability for document topics. And to give a little bit more details on that problem setup, let's say we have K number of topics and we have V words in our vocabulary, and each topic could be viewed as a probability distribution over V words. And the topic matrix A could be seen as a concatenation of topic vectors as column vectors. And the W vector is our topic proportion vector for the document. So the document generation process in this way could be nicely encaptured by the following representation. We want to generate the word distribution vector Z, from which we draw independently our word to form a document. And Z is really equal to A times W. And we're interested in W because W, our proportion vector, tells us that how much each topic is being included in a document. And our project roadmap is we first design a new self-supervised objective and propose an algorithm to recover the topic proportions. And then we formally proved our algorithm and gave theoretical bound on the errors. And around the same time, we ran lots of experiments to simulate and test algorithms' performance on different topic models. And lastly, we also applied a kernel trick to improve upon the method in previous literature. And we ran kernel regression experiments.
Now let's take a closer look at our new objective and algorithm. Our new objective for the machine learning model is called the predicting keywords objective. And just as the name suggests, under this objective, we hide keywords from a document from the model and then ask the neural network model to only look at the remaining words and then try to predict these keywords. The last layer output will then be used as the probability vector as our representation for the document. And then with the machine learning model we just trained, we can use the output to actually recover the posterior for our test documents. What we do is that we use this objective to train a neural network F and then generate an output Y. And then we can just calculate the recovered topic posterior distribution for the test documents by multiplying the pseudo inverse of A, which is our topic matrix, and the neural network's output Y. And then let's take a closer look at the proof algorithm and why it works. So we give a formal proof that the neural network's output, which we denote as f star of x, is equal to the topic matrix A multiplied by the topic posterior distribution. And we also show that our algorithm's error can have an upper bound, which means that the error will be bounded and will not be very large. And this is essentially done by relating our theorem and algorithm to the concept of condition number of our topic matrix A. And we run experiments to empirically show that the condition number A, which is denoted as kappa of A, is actually very small. So that means our error should be small. And we also run a lot of experiments to support our algorithm for recovering the topic posterior. We tried three main kinds of topic models, which are pure topic model, latent Dirichlet allocation model, and correlated topic model. And we used total variation distance between the true topic posterior and our predicted topic posterior as our metric. So as you can see from our chart, in general, the total variation distance is very small because remember, the total variation distance can have a maximum of 1. So you can see that all the variations are less than 0.25-ish. And to get these, we actually tuned a lot of hyperparameters, including the number of layers, the kinds of connections within our neural network, such as residual connections. And in general, when alpha is small, which means the topics are very different, our model can actually achieve a very good result by recovering a topic posterior that is less than 0.1 away from the true topic posterior.
Going back to the original contrastive objective from the literature, they had used a representation, which is the output of the network, that required landmark documents. And we wanted to improve upon this idea and create a representation that does not require landmark documents. And to do this, we employ something called the kernel trick, which is basically a mechanism that maps lower dimensions to higher dimensions using a inner product. So once we're able to use a kernel as our representation, which is kind of like a self-representation that only uses the documents themselves and not the landmarks, it will sort of relax the constraint of needing the landmark documents, which have special requirements typically. And then we ran some kernel regression tests to verify this idea because we want to ensure that this representation is still linearly related to the posterior as the previous landmark representation was. And through our experiments, we were able to verify this. And some next steps that we'll be taking is to further improve some of the architecture that we've been using to reduce some of the errors, and also apply our experiments and algorithms to real-world data sets and text documents. And that is all from us. Thank you.